A very good afternoon to all those present. Thank you, Dr. Lee, for very nice introductions. So, it's a great pleasure for me today to give a short talks on the research project that's carried out in my research groups. So, the title of my presentation today will be focused on the electric field driven extraction across the carrier-mediated polymer inclusion membrane. So this is a brand new project conducted in University of Basel, Switzerland since 2010, and it has been carried out until right now. So let's have a look on the principle of extraction methods for the chemical analysis. So extraction methods basically is the techniques that possess high efficiency in transferring analytes of interest from the sample matrix into a solvent of nodes or specified adsorbent in order to improve the detectability using various photographics or electrophoretics methods. So when dealing with the sample matrix with very low concentrations of analytes of interest, extraction method must be able to enrich and pre-concentrate the analytes as well as to perform cleanup procedure, which overall leads to increase of concentrations of analytes to measurable levels. So there's two major things over here. One is to enrich and pre-concentrate very trace amounts of analytes in the environmental or biological sample matrices, and also to clean up the sample matrices before you go in for any chromatography or electrophoretic separations and detections. And the recent years, by using electric field for the as a driving force for the extraction has become a very popular option. So the electrical potential is used as the main driving force in facilitating the ion transportations across the membrane separating two liquid phases. For example, electro extractions, which involve liquid extractions, but are facilitated by using electrical potentials. The electron membrane extraction, which is using hollow fiber membrane as the experiment membrane mediums, and also electrodialysis by using the ion exchange and dialysis membrane. So why we're using electric field? It allows a better control of the extraction of charged species, and the method tends to be faster than those based on passive diffusion, which is classical methods used based on chemical process. So one of the major achievements in the recent year is actually the electron membrane extractions. So this method was introduced by Professor Peterson Bjerregaard, Rasmussen, and co-workers from University of Oslo, Norway in 2006. And the extraction technique, which involves electron migrations of ionic species across what we call the supported liquid membranes. And I will explain to you what exactly is a supported liquid membrane later. And the EME allows sample cleanups and up concentration from sample volume, which is in a milliliter range, directly into an aqueous receiving phase, which is basically in the range of microliter. So you are expecting a significant enrichment of your analytes from the milliliters up to a microliter range. So this is a typical setup for the electron membrane extractions. So this is what we call the hollow fiber membrane. So there is sample solution that's present in the sample vial, and there is another acetal solution inside the lumens of the hollow fiber, and outside the membrane itself is immobilized with a thin layer of organic solvents. So the two electrode is positioned in the sample and also acetal solutions, and the applied voltage is applied to the sample and also acceptable solution to create electrical potential. So the ion will be moved across the thin layer of the organic layer, going into the acceptor phase. So the advantages of this technique is very obvious with fast extractions process, which is normally less than 10 minutes. And the selectivities can be manipulated by organic solvents and carrier, impregnated in the supported liquid membranes, and the polarity and the magnitude of applied voltages can be also modified according to the application. But there are also several disadvantages of this technique. For example, low stability of the impregnated organic layer under high agitation conditions and also high electric field environments. Low reproducibility due to the variation of organic layer. This is because when you're using these methods, you basically prepare a new hollow fiber membranes with the organic layer for each of the analysis. So the layer of the organic layer of the organic solvents is really crucial in determining the mechanisms. And thirdly, this method is very difficult to be automated, which is not possible and very difficult to be commercialized. This is a prevalence of electromembrane extractions obtained from the Web of Science using the keyword electromembrane. So it can be very obvious that in the recent year, a tremendous numbers of publications were observed, especially working on the electromembranes techniques. So in our groups, we are trying hard to find solutions, especially to solve the problems that are existing in these techniques, but still using electric field as an advantage to facilitate the extraction of the selected ions. So in 2011, we came out with a new material which is named as a polymer inclusion membrane. So this polymer inclusion membranes is purposely designed to replace the supported liquid membranes, but still maintain the advantage of using electric field as the main driving force for the ion transportation. So let's have a look what is the difference between these two membranes. So the supported liquid membrane actually is prepared by impregnating the pores of the porous hydrophobic membrane materials with an organic solvent that immiscible with water. And the liquid phase is actually bind to the supporting pores by capillary force or interfacial tension. So these kinds of binding energy is very weak and it's not stable, especially when you're working in your high agitation solutions. And the advantages of this is this entire procedure is a simultaneous extraction and re-extractions in one technological steps. As for the polymer inclusion membrane, it's actually a membrane that consists of three major components. The first one is base polymer. It provides the mechanical support for the membrane itself. The plasticizer actually provides the flexibility for the membranes. And the third component is the functional carrier. It could be an ion exchange or anion exchange carrier, depending what kinds of ion that you would like to transport. So it works as a mediator for ion transportation. So this kind of membrane is a cell-supporting membrane, and all components are well integrated into a homogeneous thin films. And the thickness can be very low, down to 10 microns, which is absolutely perfect when we are applying this membrane in a microfluidics extraction cell. And so because of the thin, firm thickness, the low diffusion coefficients problem facing by thicker membrane can be easily offset, which means the ions is able to pass through the membrane much more faster. And the strong mechanical structure that hold the immobilized carrier in extreme conditions and can create negligible loss of carrier. So basically, the ionic liquids that we immobilize in the membrane is always there. It's not going to leak or disappear, dissolve in your sample solutions, which make this membrane is possible for a multiple extraction approach. So this is how basically we prepare the polymer inclusion membrane. So we have a cellulose triestate as the polymer matrix, and so we put different kinds of plasticizer. You only use one type of plasticizer for each membrane, but you can select depending on different hydrophobicity based on the plasticizer. And these plasticizer are famous plasticizer when people are making ion selective electrodes for different kinds of ion sensors. And this is two types of functional carrier, which is anion exchange carrier that we use, which is aliquot diol-3,6, and di2-ethyl hexyl phosphate, which is a cation exchange carrier. So these three components are mixed together according to the specific proportions and put it into the dichromethane solvents for dissolving, and you pour the solution into a flat glass surface for casting overnight with closed systems. And then the next morning you just peel it off by immerse the membrane in a cold IIS water. Then you will get a membrane. So it's very simple and straightforward. So this is the SEM scans for CDA membrane without plasticizer and carrier. It's basically a porous materials. And so when immobilized with the plasticizer and the carrier, it's a total homogeneous membrane without any significant visible pores. So this is the picture of the polymer inclusion membrane. It's like a totally plastic material, very rigid, stable, and you can't actually think that this membrane is actually used for the extraction because it's just like a very normal piece of membranes. So today I'm going to talk a little bit more about the progress in our research groups focused on these technique developments. So I'm going to start with this presentation today by focusing on the very simple extraction cell setup that we developed to show people that this technique is going to work. And then we are going to show you how we are able to push the performance of this technique by switching the extraction cells from a static cells into a flow-through cells. And then I'm going to show you not only the organic ions, we're able to selectively transport inorganic anions across polymer inclusion membrane. And then how we actually manipulate the membrane compositions to affect the ion migration process, especially on the extractions of organic cations and anions. And then I'll show you a project that we performed together with University Hospital Basel to develop a very fancy single-step microflow injections analysis system for nephrocenes in human urine via on-chip electric field-driven extraction with online UV detections. So this technique does not involve any separation steps. And finally, how we are going to automate the entire process and then couple to LCMS systems for trace analysis of phenoxy acetic acid herbicides in environmental water samples. So first of all, this is a diagram showing our very first setup, which consists of two PDFE blocks. And the membrane basically is cut and sandwiched between these blue blocks. And over here is the sample solution, which contains 20 milliliter of samples. and this is 750 microliter of acceptor solution. So we are expecting all the analyte is able to migrate from the sample phase across the membrane into the acceptor phase. And after the extractions, we are going to quantify the amounts of analytes inside the acceptor phase by using capillary electrophoresis. So this is the extraction cell setup, which is made from PDFE. And we have voltage supplies from 0 to 30 volts used to regulate a high voltage module to generate voltage from 0 to 1500 volts. And there is a small circuitry here is used to monitor the currents that generated by the ion migration from the donor to the acceptor phase. And this power supply is to supply the power for the operation amplifier used for the ion monitoring. So for any kinds of new methods, normally we are going to show you a proof of concept experiment. So one octane sulfonic acid was used as the model analyte and spiked in the sample solutions in 20 mL of 0.1 millimolar potassium chloride. So this shows the electrophoregrams for the octane sulfonate contents in sample as well as in the acceptor phase. So this is obtained by using a capillary electrophoresis with contactless conductivity detector. So you can see that the amounts of octane sulfonate acid in the sample phase reduced tremendously along the extraction times. And from the beginning of nothing present in the acceptor phase, the amounts of octane sulfonates increased tremendously. And the different scale for the signals basically represent that there is up concentrations for the amounts of the octane sulfonate acids from the sample to the donor phase. So from these observations, we able to prove that the carrier-assisted transport of the selected anion across the membrane under the influence of the electric field is indeed possible. So we are very excited. I remember I repeat this experiment for more than 50 times just to make sure that everything is working before we proceed to the other optimizations. And after the optimization process, this is the overall results by showing 3 different kinds of alkyl sulfonate acids spiked in these samples. And we perform the extractions at 3 different time intervals at 5, 10, 20 minutes. And this is the limit of detections for each of the extractions. And surprisingly, the percentage of analyte concentration extracted, what we know as the recovery, is actually always the same, independence of analyte concentration in donor phase. Which means, for example, if you perform a 5-minute extraction by putting different range of concentration into the sample solutions, you are always receiving a recovery at 60%. You won't see a phenomenon whereby if you're putting more, the analytes will migrate more. No. And since the recovery is always consistent, this is extremely good if you like to develop an extraction method. And for this approach, it's not necessary to wait for completeness of extraction. As long as the desired concentration level is achieved, which means if you're only interested to detect propane sulfonate up to 20 nanogram per milliliter, you can just perform an extraction in 5 minutes. It's not necessary for you to perform extraction until 20 minutes to achieve a 5 nanogram per milliliter LOD. So this provides a flexibility for the extractions options, because everyone would like to have a fast extraction technique. So I'm going to move on to show you how actually we able to push the performance of this approach by simply changing the extraction cell into a flow-through cell. So this project is not conducted only by myself. It's actually also conducted by my master student, Simone. So Simone is a very hardworking German lady. She performed this experiment by using a brand new flow cell chamber, which consists of 500 microliter of donor volumes and also only 100 microliter of acceptor volume. So the sample solution now is continuously pumped into the donor phase chamber continuously, and the voltage is applied continuously for the extractions. So right now you can pump in as much as you want the sample solution, but still maintain 100 microliter of your acceptor volume, which means you are enlarging the enrichment factor because of the sample to acceptor volume ratio. And so in this project, she focused on detecting two analytes, which is glyphosate and its major metabolites, amino-metal-phosphonic acid. And the sample is actually 10 milliliter, and so the flow rate is set at 1 milliliter per minute, which is actually 10 minutes of extractions. And the acceptor phase is in a stagnant position, which is only 100 microliter, and the applied voltage that she uses is 1500 volts. So this is a very important electrophotogram that's showing the first one is the starting samples that containing glyphosate and NPA at 100 nanogram per milliliter. This is without any extraction, there's no treatment at all. And after the extractions, we actually collect the sample after extractions. You can see that the amounts of the NPA disappears, and there's only very tiny amounts of glyphosate still left in the sample solutions. But at the meantime, in the receiving solution, a huge analyte peaks of glyphosate and NPA were detected, which means all the analytes in a 10 milliliter sample is all migrated across the membrane into the small amount of acceptor solutions, and all is detected by the capillary electrophoresis. So this is a graph showing the influence of the applied voltage. If you apply only 0 volts by turning on the pump to pump the samples, by applying no voltage, basically there is nothing that you will see in the acceptor solutions. But the amounts of the glyphosate and NPA that's detected in the acceptor solutions increase tremendously together with the increase of the applied voltage. And eventually it reaches equilibrium state, which is when the applied voltage is above 1000 volts. So we also perform a test to check how the membrane perform if we're using a single membrane to perform the 20 batches of samples. So you can see that there are 2 batches of samples. One is filtered river water samples. The second one is unfiltered river water samples. The recovery for 20 replicates actually is quite consistent, but the best is actually up to 10 ounces, and there's a slight decrease on the performance of the membrane. But on the other hand, for the unfiltered samples, it's only maintained for 5 times. And then the performance of the membrane starts to decrease continuously. this is due to the microparticles that present in the river water. It started to accumulate on the surface of the membrane. And then after 10 times of analysis, we can see that on the membrane surface, there are already some particles that deposited on the surface, which reduce the active sites of the membrane that allows the ion to migrate. But this is very simple. We just put a membrane filter along the sample tubing during the sample flow-in systems. So it's not very tedious that you require a lot of manual works to filter the samples. And so this is a comparison result that using a static cells and also the continuous flow-through cells. So the linear range is much better by using flow-through cells. The LOD is actually much improved. Now it's down to picogram per milliliters. And also the enrichment factor is much more higher, from 26 up to right now to 95. But we also try to flow 20 milliliter samples, which can increase the enrichment factor up to 200s. But it will double up your extraction times. So it's also depending what kinds of LOD you are looking for. So if you are looking for some LOD which is lower than this, you can increase the sample from 10 to 15 or 20 in order to get a lower limit of detections. So extraction of inorganic anion is normally very tedious, because it involves using ion exchange or SPE, solid phase extractions, or using liquid extractions, but involve depolarization or complexing procedure. But this approach is nothing with depolarization. It's a straightforward extractions of inorganic anion across the membrane. So this project was conducted by my master student, Yulia. So Yulia performs these experiments in a brand new extraction node, which is much more smaller compared to the previous one. And the sample is flowed in through the syringe pump into the very tiny extraction channels. And then in the receiving site, the receiving solution was actually flowed through into the chamber by using a syringe pump as well. And the accepted solution is remain stagnant during the extraction, but the sample is continuously pumped through. The membrane size is much smaller right now, with only 30 × 6 millimeter. And after the extraction, the accepted solution was injected directly to capillary electrophoresis for quantification. So this is the extraction cell, which is actually pretty small. And you probably can't see very obvious that actually the membrane is already placed on the top. And these PMMA materials is actually clamp each other with the membrane in the interface, and the samples is actually flow through continuously, and this one is going to the waste. And this is the acceptor solution that positioned in your acceptor channel, but remains stagnant during the extraction. And this is actually the electrode that we put directly into the chamber, directly from here all the way to the chamber, to provide the applied voltage. So this is the summarized result, but I'm going to explain to you a little bit details. Yulia actually prepared 7 different kinds of membranes, which is with always same amounts of CTA, which is the cellulose triacetate, but she varied the amounts of plasticizer and the aliquots in each of the membrane. So the membrane number 1 contains no carrier at all. Membrane number 7 contains the highest amount of carrier. And for the table number 2, she designed A to H experiment, which is by checking different lipophilicity and ions. So there is a phosphate, which is the lowest lipophilicity, followed by sulfate. So for experiment A, we want to extract phosphate. Experiment B, the nitrate is the target analyte. For experiment C is bromide, followed by perchlorate. And for the experiment E, we want to extract sulfate, but we're putting lipophilic ions as the background solution. So the sulfate, nitrate, bromide, thiocyanate is the target analytes in experiment E to H. So it's not necessary to look at all the results. You just focus on 2. The first one is experiment D. If you want to extract sulfate, which is low lipophilicity, you look at the result of sulfate detected in the receiving solution. The membrane number 1, which contains no aliquot, resulted in the highest amounts of sulfate detected in the receiving solutions. But if you're using a membrane with 40% of aliquot, the sulfate is disappeared, which means it still remain in the sample solution or stay inside the membrane and it's not going through in the accepted solutions. But on the other hand, if you look at experiment E, if you want perchlorate as the background and the sulfate as the target, now the opposite phenomena is also observed. You have to use a membrane with 40% of aliquots in order to get the highest amounts of sulfates to detected in the solutions. For this one, I think I made a mistake. Perchlorate is the target, but for this one, sulfate is the target. So we are very surprised with these results because we didn't expect that because of slight difference in the lipophilicity and you simply change a little bit of the membrane composition, it resulted in a totally opposite migration profile for different kinds of inorganic anions. So this is something very interesting and it should be further studies to understand the mechanisms. So Julia tried to show some useful approach by detecting perchlorate in the drinking water samples. Perchlorate right now is very popular in the trace analysis because recently European Union has included perchlorate standards in the drinking waters. So we need to develop a very, very useful method to do a trace analysis of perchlorate in the drinking water samples. So this is the electrophorograms of perchlorate enriched in the acceptor phase using different combinations of sample and also the different amounts of perchlorate. Actually, similar peaks is observed, but when you look at the combinations, number 8 is actually 2 pair of samples by using with 0.05 micromolar of perchlorate present. But for number B is 10 milliliter of samples, but now the amount of perchlorate is much lower, which is only 0.01. But it still resulted in similar sensitivity in the capillary electrophoresis, which means if you want to detect very trace amounts of perchlorate, you can simply increase the amount of sample that you inject into the solution, into the donor phase extraction chamber. But at the meantime, you also have to consider that if you're putting more samples, it takes more time. So these have to be compromised between the time and also the detection limits. And then I would like to show you some fundamental study on the membrane compositions how actually you're able to use, by changing the membrane compositions, to affect the migrations mechanism of the organic cations and anions across the membrane. So we're back to the diagrams. So for this one, it's always consistent, so there's nothing we can do. But for the plasticizer, if you look through the ion-selective electro research, there are a series of like maybe more than 50 kinds of plasticizers that you can use. So this is become our main interest for Carrier. Carrier basically is just help you to transport the ion. So our focus will be putting on into the effect of the plasticizer at the present state. So we chose 4 types of plasticizer, which is very less hydrophobic FPNE, a medium hydrophobicity MPOE, 7.8 log p-value BHA, and also the most hydrophobic THP plasticizer as our testing material. So the setup is similar to the previous one, and you can see for the extraction of organic anions, very interestingly, for each of the plasticizer that you use, they only shows optimum conditions at different amounts of plasticizer. For example, for the less hydrophobicity MPNE with a log p-value of 2.7, they only perform the best when you use 8 milligrams of plasticizer in the membrane. But on the other hand, the most hydrophobic THP, you only requires a very tiny amount of 2 milligrams to be present in the membranes. So similar result was also observed for carbon 7 heptane sulfonates, and also for the carbon 10 decane sulfonate migrations. So it gives us a clue that if you accidentally using THP but putting too much of plasticizer in the membrane, you actually resulted in a negative effect to your migration profiles. So this is actually very important to know how much of the plasticizer you need to put into the membranes. As for the migration of cations, it's also the same. THP resulted in the highest performance, followed by BHA, MPOE, and FPNE. So it can be concluded that we should actually use the most hydrophobic plasticizer to use as the membrane material instead of less hydrophobic plasticizers. And so move on, I will show you a very simple or fancy approach that we designed together with the hospitals in Basel City to detect naproxen drugs in human urines via on-chip electric field extractions. So in this approach, there will be no separation step. For the previous one, we always analyze the acceptance solution using capillary-like forces, but this one, there's no separation step involved. So this is a very small approach that the sample is, the background solution is continuously flow through the injection valve into the extraction cell and detected by UV detector number 1, which is set at 332 nanometer, which is the detection wavelength for the naproxen. And then the receiving solution is also flow through into the cells and remain static during the extractions. And applied voltage, the sample is actually injected through the 6-way injector valve and flow through the extraction cell, and the applied voltage is turned on to push all the analytes across the membrane into the receiving. And then after the extractions, the microsyringe pump for receiving solution is turned on to purge all the tiny amounts of enriched analytes go through the UV detector for direct quantifications. So the membrane that we use is optimized condition over here. The membrane is only 15 microns. And so for these examples, we put 10 microliter of human urine samples that contain 50 micromolar of naproxenes in the 0.1 millimolar sodium perchlorate background solutions. And the receiving solution over here is only 2 microliter because this is a specially designed micro flow cell which only have 2 microliter volumes, and the applied voltage is only 150 volts during the extractions. So this is the result that's showing first. You look at the detector number 1 over here. So the amounts of naproxene in the beginning, without turn on the voltage, the sensitivity is like this height. But once you turn on the extraction voltage, the peak sensitivity for the naproxene reduced quite a lot, which means a big portion of naproxene is already migrated into the membrane and maybe across the membrane. And on the other hand, after the extraction, we turn on the receiving background solution pump to purge the enriched analytes. We noticed that a huge piece of the naproxene signals was obtained. And so one of the measure parameter is what is the flow rate, the purging flow rates that we should use. Because if you're using a too low purging flow rate, there is a dispersion of your enriched analytes along the tubes, which causing a very broad UV spectrum signals. And if you're using a too high purging rate, it actually resulted a very sharp peaks, but the peak area and the sensitivity will be much lower. So this is the summarized result by using purging rate of 3 microliter per minute. And we able to form a very linear calibrations by injecting samples containing 5 to 200 micromolar of naproxene in human urine. And the LOD is down to 2 micromolar, which is sufficient enough for clinical analysis approach and a very good recovery from 92 to 95%. And most importantly, the time that starting from the sample injection to detection is only 10 minutes. So this is a very specific approach that only focuses on naproxene in the human urine samples. Okay, last but not least, I'm going to show you how actually we try to think about future, how we should sell this technique. So we automate the entire procedure, and then we showing a useful approach to analyze the phenoxyacetic acid herbicides in the river water sample coupled with the LCMS systems. So this is our schematic diagrams. We have a programmable syringe pumps that used to withdraw different kinds of sample acceptor solutions into the extraction chamber. And we have a selection valve which is fully controllable